Welcome to our Azure Incident Retrospective. I'm David Steele.
I'm Sami Kuba. We work in the Azure Communications team.
In addition to providing a written post-incident review after major outages, we also now host these retrospective conversations.
You're about to watch a recording of a live stream where we invited impacted customers through Azure Service Health to join our panel of experts in a live Q&A.
We had a conversation about reliability as a shared responsibility, so this includes our learnings at Microsoft, as well as guidance for customers and partners to be more resilient.
We hope you enjoy the conversation that follows. Super, thank you. And today we'll be focusing on an event that took place on the 16th of September in East US. Typically, when this event first happened, it was characterized for the longest time as a SQL database outage. As we've learned more and more, and we've published our PIR and our learnings, you'll see that while SQL were an impacted service, this was triggered by a data center event, and a compute were involved, and there were a couple other services that were impacted as well. But this is going to be a very interesting conversation.
Very good. And to help our conversation be interesting, let's introduce our panel for today. So we have 4 speakers joining us, starting with Krista Markgraf, the General Manager of our data center operations for the East region in the US.
We have Igal Figlin, our Vice President of Azure Host and Core Fundamentals.
Also joining us is Jason Whitehorn, our Partner Engineering Manager for firmware from our hardware infrastructure team.
And lastly, but certainly not least, Asad Khan, our Vice President of Azure SQL Databases. Krista, I'm going to come over to you if I can first. While this wasn't the root cause, was never a data center issue, but you certainly were the trigger of this entire thing. Reading the PIR and kind of understanding this was a 1.9 second power blip, and it had a huge cascading event. Power blips, surely they're not that uncommon in the data center world. What's supposed to happen during a power blip?
Yeah, great question. First of all, thank you so much. And good morning. And I do want to start off by saying that first and foremost, we exist to support your businesses and provide unbending service and availability to you. And this outage affected your businesses. So what's critically important for us is to really take this event and make sure that we use it so that we can learn and make it, make us stronger and better for you. But this power hiccup occurred in our, as you said, our US East region, in one of our data centers, and it impacted a half of a data hall. What we saw is multiple scale units experienced this loss of power. And, to your question, while it's not uncommon for data centers to experience an intermittent loss of power from time to time, one of the ways that we protect against this is by leveraging uninterruptible power supplies, or UPS. And the role of the UPS is to provide stable power to infrastructure during short periods of time when you see these power fluctuations. And, although we have redundant UPS systems in place for added resilience, this incident was initially triggered by a UPS rectifier failure on the primary UPS.
Our kind of starting point to the story, a UPS rectifier failure. I'd love to understand what that means, because as I'm reading through the post-incident review, I see UPS, we talk about STS, we've got lots of TLAs, 3-letter acronyms. Krista, could you help me how would I explain this to my mom if I wanted to explain to her what a rectifier is, how that failed, and especially that cascade to the broader scale units losing power here?
Sure. Yeah, and I talked about the primary UPS a bit ago. So let's call that energy source 1. And then you have a secondary UPS, which is energy source 2. And as I noted a bit ago, we had a rectifier failure on that primary UPS, which triggered the event. And by the way, what a rectifier does is it converts alternating current, or AC, to direct current, which is DC. So because of the failure, the customer load actually transferred from power source 1 to power source 2. And these loads are transferred via a static transfer switch, also known as an STS. An STS is designed to transfer critical loads between independent power sources. So after that load transferred from source 1 to source 2, the load then transferred back to source 1. And while that primary UPS on source 1 was available, it was not stable enough to support the load. Now, what was supposed to happen next is that load was supposed to immediately transfer back from source 1 to source 2 a second time, and it didn't do that. And the reason for that was due to the way in which that STS was programmed. So the logic inside the STS contains a 5-second delay. And the reason for that is is to stagger those power transfers when there are multiple power transfers happening in a short period of time. But this logic kept the load from transferring back to source 2 before the load was dropped. So this scenario of load transfers sort of to and from the degraded UPS over a short period of time, that was not accounted for in the design. So, what happens next is all the downstream power distribution units, or PDUs, were de-energized and the load was dropped for that 1.9 seconds that you mentioned at the beginning. Now 1.9 seconds goes by, and then the PDUs are re-energized for a final time on source 2. Now, if you think about, this was a logic issue, right? If you think about the goal of equipment design, the goal is to provide for the optimal level of safety, reliability, efficiency. So when you bring a design forward, the intent is to refine it so that you can provide benefits, right? And even improve operations. As I mentioned earlier, that logic inside the STS contained that 5-second delay to stagger those power transfers. But unfortunately, if you look at this specific combination of events, this specific design, it doesn't provide that uninterrupted power that was needed. So as we think about immediate next steps, we've implemented, immediate repairs. We've replaced that failed rectifier inside the UPS. We sent that failed rectifier off to the manufacturer, and they're working on a forensic analysis, and we expect to get those results back shortly.
Magic, thank you very much, Krista. And while I'm sure the rectifier failure analysis will take some time, and they'll come back with forensics, in the meantime, how do you deal with the updates from the STS piece? So the logic of transferring or not transferring, are those easy things to do in the interim in case another rectifier fails at some point in time?
Yeah, so a couple things here to talk about. So first of all, we've changed the settings on these STSs from what we call auto to manual retransfer. So this couldn't happen again. So that load from source 2 couldn't go back to source 1 unless that source 1 was completely stable and healthy. So that's the first thing. But additionally, we are reviewing STS transfer logic across all of our data centers in our fleet, because we want to make sure there isn't some sort of a pre-programmed delay that would put our load at risk again. And we've made it through a majority of this exercise for our data centers, and we're going to continue to make this a priority and make it urgent. We also want to be comprehensive, and we really want to make sure that we aren't solving one problem and then unintentionally creating another. And then finally, we're looking to see, are there broader and deeper changes that we want to even review? We talked about design before, right? Are there broader changes that we want to make as we look at STS logic across the fleet, just to make sure that, again, it's about providing the most resilient outcomes based on our experiences?
Got it. That's great to hear, Krista. Thanks for running us through both the long-term analysis and the shorter-term repairs. But one last question for you. We've seen several different data center issues that were kind of triggered by power incidents, not always in the US, not always in that certain region. But generally speaking, is there a theme or a pattern that your team is noticing here, or are these quite kind of separate events?
Yeah, this is, I wouldn't say there's a specific pattern here. Power events can happen for a lot of different reasons. But with that said, we take any power event very seriously, and the implications go beyond, just this piece of equipment or just this data center, because we're, as I kind of started off with this commitment, we're looking to get better and better across the fleet. So just to give you a sense of some of the forward improvement plans for, from a data center perspective, as Microsoft embraces that growth mindset. So the idea is, for us, we should never be done improving. We should be learning all the time, seeking to get better. This is a continuous improvement that just, it doesn't stop. So it's not just about reviewing equipment components and lineups. It's about reviewing and refining things like operating procedures and training, and looking for those opportunities to harden operations even more, because we really want to ensure that we have the highest quality approach in everything that we do.
Super. Thank you very much, Krista. And I like the fact, as the world keeps changing, we need to keep current. Igal, if we fast forward 1.9 seconds later, which isn't a huge amount of time, I know, as Krista said, we account for power blips and so on, and I'm sure compute does the same thing. How is compute usually designed to recover from a power blip, and what happened this time?
Let me first start with focusing on what we are generally doing in my team in order to deal with situations like that and similar situations. We are thinking about overall platform design, recovery, resiliency, all the accelerators that we have in our system in order to facilitate both normal operations and similar situations. Generally, we are prepared for the power outages, and when power outage occurs and power is restored, the systems are expected to come back automatically relatively quickly. And a large part of the system did come back automatically fairly quickly. Unfortunately, part of the system did not behave as we expected. Some part of the system did not recover because of a few gaps that we saw. First one starts with insufficient telemetry, insufficient alerts that we are working on, and we will add. When part of the system recovered, some other part of the system assumed that we are running normally and did not facilitate the rest of the recovery in the way it should have done. So essentially what we observed is that part of the system thought that we are recovered and the rate of the recovery should not be expedited. We expected normal operation with lower rate of change. So we do have edge conditions during the recovery when the power comes up unevenly or in certain sequence where we need to optimize the operations that we have. The last but not least, the underlying code that handles BIOS did not work as expected. We expected a certain operation during the recovery, during the start of the node, and we observed different behaviors than what we expected. Let me maybe take a step back and say that we are constantly testing our systems, both for recovery and for zonal resiliency, and those two are tightly related. And when I say zonal resiliency, I mean not just the entire zone down, it's also part of the zone being recovered, part of the zone down and being recovered. However, in this specific case, the tests that we performed in the past were not sufficient to detect this situation. And so we are taking a few sets of fixes to avoid similar situation in the future. I think the first one is obviously about how do we detect this condition very clearly? How do we make sure that we know that the system is recovering, partially recovered? How do we make sure that rate of the recovery can continue and retries can be performed in the right way during similar power events? The other part is how do we detect those edge conditions? How do we identify, alert on those edge conditions, involve faster the right people, the right designated responsible individuals in the team, but also restart platform components, platform mechanisms in the right way. The last but not least, as a learning of this power outage, we would like to set up a new set of exercises internally in the team, let's call them drills, where we exercise those conditions which are not trivial, not just vanilla power recovery, but those edge conditions where we can see more complicated sequences, more complicated recoveries, and try them out both as part of our operations, of course without customer impact, but in dedicated environments, but also as a part of the certification of any new release for the components that we are changing. I think it's important to note that Azure, as any cloud service provider, is constantly changing, adding new features, becoming more secure, adding additional mechanisms, keeping up with customer requirements on scale, performance, reliability. And in order to achieve that, as those components rev up, we will continue validating that every component can sustain the expected recovery behavior, can perform the right behavior in similar situations.
Thank you, Igal. That's a great summary of all the different things that are happening at the moment to make sure that we can anticipate and respond to these kinds of things appropriately. So that's a great foundation for this conversation. Returning to this specific incident, I understand that while troubleshooting, some individual nodes reboots kind of helped fix things, other kind of bulk reboots didn't quite help fix things. We explained in the post-incident review that some of those bulk reboots were failing because of a safety check. So I wanted to understand that a bit more from you and hear about the learnings specifically around that.
Yeah, so one of the safety checks that we have has to do with the rate of recovery, essentially how many physical nodes, physical machines are going through the change. And during normal operation, we want to limit that rate to ensure that the system behaves in an expected way. In this specific situation, we should have removed those limits, and we are removing limits in those situations. But in this specific case, we did not detect that condition, and those limits were enforced, which not just slowed down the recovery, but essentially put it to halt until we were able to detect that those limits kicked in and unblock the system from recovery. And this is probably one of the main focus areas. How do we make sure that we detect that the system is still recovering and we are not enforcing those limits?
Super. Igal, as SQL were communicating during this incident, and as we've reviewed in the post-incident review, a huge amount of time was spent troubleshooting and trying to find the issue. Once we found the issue, once we understood, okay, there was a BIOS thing and the bulk reboots, how quick was our recovery? Is that something that is that room for improvement, or was our recovery rapid?
Once we identified the issue, it was pretty quick. But the question that I would like to ask ourselves is why it took us so much time to identify this condition. And telemetry is probably, the telemetry dimension probably is the most important aspect here. We need to make sure that the alerts we are getting are the exact specific pointing to the right component, where the recovery is blocked, what is impacting which part of the system is taking the decision not to recover. And this is the telemetry improvement, the alert improvement that we are going to take. And just to be clear, we are not waiting. This is critical for us. We are not waiting for another outage. We have set essentially 3 steps in recovery. First step, mitigating the incident that was performed during the incident itself. The second step, immediate fixes that we are taking, and we are expecting to complete them within the next weeks. By mid-October, we would like to be behind all those immediate repair items. And I think long-term, all those drills, those exercises, we would like to do them on the ongoing, to perform them on the ongoing basis. So not just recovering from this specific incident, but making sure that we are always ready for incidents like that.
That's great to hear. Thank you, Igal, for that summary from the compute side of things. Now we're talking about kind of having to reboot to bring it back online. So Jason, I wanted to turn to you because one of the reasons that we had to do those forced reboots was because of this known BIOS issue. So I wanted to start with you and say, well, what did we know in advance, and how do we socialize that kind of information internally?
Yeah, great question. So let me start by talking about the bug itself. You may have seen this behavior on your PC, but the way that most PC architecture systems work is they have a boot order that they go through when they start up. And the default boot order inside of Azure is for machines to boot to Pixie servers. And the design is for them to simply repeat and continue to try booting to Pixie servers until those servers are available. What happened in this case is that if the switches come up, the switches connected to the nodes before the Pixie servers, it'll start trying those Pixie servers and it will time out and it will return to the setup screen. So that's what happened in this case. That was the known issue that we ran into. This issue has been fixed, but the fix has not been deployed to all of the machines in the data center.
Jason, I know that in the PIR, you've detailed about kind of it's in rollout at the moment. Is there a trade-off between taking the latest update of this kind of BIOS fix, and does each service have control over this? How do we manage these kind of BIOS updates for known issues?
Yeah, that's a great question. So across the fleet, we have customers with long-running virtual machines. Of course, customers vary, but many workloads do need to run for months at a time. Our primary way to deploy updates that require a reboot, which this kind of update does require, is to wait for those machines to be empty. As VMs are started and shut down, some nodes will become empty. And when that happens, we'll reboot the machines and we'll apply the update. We do have some other ways to do those deployments, but this is our most common way. And this creates a tension between the need to deploy fixes and the desire to keep customer workloads running. And so what happened in this case is that many of the nodes, in fact, most of the nodes in this cluster had been updated, but not all of them, or of this type had been updated, but not all of them. And those which had not been updated hit the issue.
Super. When I think about, and thank you very much for explaining this to me, when we have a known issue, this is the way I would understand it, but tell me if I'm wrong. We have a known issue with a BIOS thing. And so what happens is we'll stage it. So the next time the node reboots, it's going to go and fetch the latest one because that's what it should do. In the spirit of never letting an outage go to waste, when these nodes rebooted, did they all grab the latest BIOS firmware and flash themselves and move forward, or were they still reverting to the old one?
Yeah, that's also a good question. It's important to talk about how we do deployments in the fleet. We do have safe deployment practices, which we use for all of our deployments. And the way they work is we'll start by deploying to some small portion of the fleet, and then we'll gather feedback on how that's going. And then we'll go to a broader set of the fleet and so on. That enables that deployment to be safe. If we program the flash of devices that are never running the new code until an emergency happens, like a power outage, we do risk the possibility of the machines being completely dead. At least in this case, we were able to reboot the machines and they were back in service after some period of time. If we didn't follow the SDP or the safe deployment practices, those machines could be down for multiple days until we could visit the nodes. So while we are absolutely investigating ways to do this more quickly, our default action is never to blindly program new code on devices without the ability to retrieve health signals and see how that's going.
That's a great way to explain the kind of pros and cons of the different approaches here, and glad to hear that we're treating it cautiously. Thank you, Jason. Asad, I wanted to turn to you to understand some of the SQL impact here. For most of the time we were communicating about this incident, we were talking about it as a SQL outage because you were kind of first to detect and first to communicate about this. Now we've understood some of the broader context of the incident. When we zoom into SQL, I want to understand, we said most customers who were using zonally resilient databases weren't impacted by that. So customers who had kind of expected that there could be zonal failures, mostly were okay, but I understand not everyone was okay.
Yeah, no, that's a good question, and I think that, so as you said, like when the power outage happened, and from there, as Krista covered and Egal and Jason, when the hardware started to come back online, most of the customers saw the recovery on the SQL side. So to be specific, only 3% of the nodes had the BIOS issue in that region. The rest of the 97% of the SQL customers were back online as soon as we recovered from the power outage. Now, within those 3%, like we spent a lot of time today talking about what caused that issue on the BIOS side. I want to spend a few minutes in terms of like these things can happen, and a lot of the customers are running their mission critical applications on SQL. So how do they protect themselves? So there are two key things. One is that the availability zones. We want to ensure that all customers who are running their production workloads are using the multiple availability zones in Azure. So in this case, anybody who was using or had deployed their databases across multiple availability zones, they did not get impacted. What you are talking about is that there was 1.3% of the customers who were using the proxy connection that got impacted. And even for that 1.3%, we took the learning, we applied the fix, and that fix is already available worldwide at this point. So it is very, with confidence, I can say that having your databases deployed across multiple availability zones is super, super important. The second thing is that although in this case, only one availability zone was impacted, but for a minute, assume that even if there are multiple availability zones impacted, then that is where on the database sides, the DR or the disaster recovery setup is super important. And SQL has obviously one of the most sophisticated offering when it comes to you can have the geo replication for a single database, or you can have the auto failover groups for a set of databases. And again, that's where we work with the customers to ensure that they do their DR drills so that even if their full region is down, they can do a failover into a different region and have the availability back for their apps to be up and running. So those are the two key points I will say. I know we spend most of the time in trying to understand why it happened, but even if it happens, how can customer protect themselves? Those are the two key points to land.
Super. Thank you very much, Asad. I want to touch on one point. We mentioned in this incident there were delays in the auto failover. Now, this was also happened in a previous outage, I think, on the Australia region. We had improvements that are coming out in October. How long should the auto failover take for customers?
Yeah, so that's a really good point, and again, learning for us as well. So just to spend a minute, basically what auto failover groups allows you is that you can take a set of databases and you can say that in case of a disaster, failover to a different region. What signals are used for deciding that thing? Customers can use and decide on their own when to failover, or they say, I want to make it auto and Microsoft should failover when there's a disaster. Now, the SLA is 1 hour, and it definitely took us longer than that because we have to also ensure that there is the disaster is longer, and it is better to fail over the entire set to a different data center, because often what happens is that there is an entire stack of application that is running, and even if you fail over the database, if the entire stack is still running in the other data center, it can create problem. But as you said, Sammy, good learning for us as well. We need to improve when it comes to the auto DR. If we are promising to the customer that we will do the failover for them, then we need to ensure that that happens in a timely manner. And in this incident, it did take the SQL team longer to do the auto failover.
Right. Thank you, Asad. Thank you for running us through the technology kind of improvements as well as the people and process improvements for pulling that auto failover lever here. I'm mindful we're running out of time, but I've saved one last question for my co-host here. Sammy runs our incident comms team. So at this junction, I'll often turn to Sammy and I'll say, from a comms perspective, keeping customers informed, how did we do during this incident?
It's a great question, David. For the most part, as we mentioned earlier, and in the PIR, Brain, which is our auto communications, triggered pretty much immediately for SQL, and SQL customers were kept up to date. We had a big gap in compute, so for virtual machine customers using virtual machines wouldn't have any communication. At one period down the line, we realized our external signal didn't quite match up with what we had scoped, and at that point in time, we elevated to the status page, which is only when we really use that page when we can't grasp who's impacted or impacted is spreading rapidly. We went to the status page, and then we understood that service bus and event hubs were also impacted as well. It was interesting to find out that it wasn't their zonal resilient services that were impacted. So if you were using a service bus that was zonally configured, you were not impacted. If you were using virtual machines, you weren't impacted as well. But it was only after the fact that we realized that we went broad, but we never actually targeted those customers who were impacted. Our team is working very closely with Igal's team to ensure that Brain, the auto communication mechanisms, will be able to withstand outages even when the clusters go down. The health kind of triggers should be firing, and that's coupled with our auto communication as well.
Thank you for watching this Azure Incident Retrospective.
At the scale of which our cloud operates at, incidents are inevitable.
Just as Microsoft is always learning and improving, we hope our customers and partners can learn from these too, and provide a lot of reliability guidance through the Azure well-architected framework.
To ensure that you get posted incident reviews after an outage and invites to join these live stream Q&A sessions, please ensure that you have Azure Service Health Alert set up.
We really focused on being as transparent as possible and showing up and being accountable after these major incidents.
Whether it's an outage, a security, or a privacy event, Microsoft is investing heavily in these events to ensure that we earn, maintain, and at times rebuild your trust. Thanks for joining us.